do the best we can, okay? We'll get started, even though I wanted to show you some very nice applets that illustrate the topics we're talking about. There's some beautiful things on the web these days. As I was talking with James, saying that there's almost too many. It's hard to find the best one. But I have a few that I think are very demonstrative. So let me begin first by, maybe we can turn the music down a bit. That Hebrides overture reminds me of Waves, which the composer Mendelssohn saw when he visited Scotland, and it was inspired to write that kind of flowing music. To quickly summarize what we said last time, it had to do with how quantum ideas first got into physics, how we first understood it. And the idea was that we know, or it was known already in the 1870s, that heat was the motion of particles. In particular, what was well understood was the simplest case, namely a gas. In a gas, the particles are not interacting very strongly, so you can think of them as being free and just moving around with some speed. And some very smart people, Maxwell and Boltzmann, that's our same Maxwell of electromagnetism, and Boltzmann, had gotten a theory considering the number of particles at a certain speed, and they got a kind of a distribution. They figured out how particles were moving. Okay. And if there was a distribution of speeds, as you might imagine, it's kind of a random things. They're bouncing off each other. They're bouncing off the walls. Some of the particles are moving very slowly. Some of them are moving quite fast. And there's a kind of an average speed. Over here someplace, the average. And that extended all the way out to high speeds. But on the other hand, that distribution varied with temperature, such that if you lowered the temperature, the particles would slow down. The total, in the case of a gas, the total number of particles is the same. You just have a bottle of gas with a certain number of molecules, and what would happen is simply that the average would go down as the temperature was low compared to a high temperature. I hope that those ideas are familiar to you. It's a very, very important idea. It seems maybe seems obvious to us now after you've been through college and high school. But in the days of 1800, it was completely unknown what heat was. People realized that you had a hot thing and a cold thing, heat would flow, and they imagined it some kind of a fluid. In fact, they even had a name for it, phlogiston. You know, that's flowing from one body to the other when you touch them together. It turns out it's not that. Really what it is, it's the contact, and the thing on one side is moving fast, the thing on the other side is moving slowly. They bump into each other, and the bumping sort of moves along, and that's the flow of heat, as we now understand it. And we have a tremendous amount of evidence that that's the correct picture. Or we can actually visualize in various experiments how things slow down as they cool. So that's the picture here. Now, the idea of why you need a quantum to explain things is that if you have this kind of picture, turns out that the average energy of the particle is proportional to the temperature, the average. As I tried to show you, you can show this from just the idea that these gas particles are moving, and so they're bouncing against the walls. That's what creates the pressure inside a gas. When you blow up a balloon, the fact that the balloon is stretched, It's because the molecules inside are moving fast. And if you put in enough molecules at our temperature, they will expand the balloon. So and from that idea, you get a pressure and in the volume, and that is PV equals nRT, number of moles. James, they're all there now? Oh, that is super. Let me see here. Here we go. This is a very wonderful applet from Oklahoma State is where I found it. So what we can do with this very nicely, if I can avoid crashing, we can, for example, where's my arrow? Arrow. Huh. Oh, here we go. I can, for example, I have here the possibility of two different kinds of gases, helium and neon. So far they've shown me helium. Let me see if I can. Gee. I should bring my own computer. It's much more comfortable. And in principle, I can increase the amount of helium. Oh, what did I do? So I want to just, if I can, increase the amount of helium in this, if it'll do it for me. No, it doesn't want to do it. Gee whiz. All right, but what I can do is very... Oh, and here's what's nice about this. It actually shows a graph of the speeds here. There aren't that many particles. I was wanted to add more. Maybe it will finally be nice. No. Okay. Okay, so here are the particles kicking around. If I lower the temperature, I think you can see that this average will lower. Let's see if it will allow me to do that. As you see, oh, for some reason the number of particles went up. That's amazing. Okay, but at low temperatures, they're moving rather slowly with a rather slow average. Now, here's the point. If I have the average energy is just proportional to the temperature. But why you need a quantum is that if your energy level were over here, if you had a quantum energy level, and it was over here, you see that at this temperature, there are no particles energetic enough to excite, to get up to this energy level here. So we would say that an energy level over here, let's say over this letter S, that would be sort of frozen out. But if we can increase the temperature, which I'll do if it'll allow me, I'm increasing the temperature. Now you see that if I increase it enough, at the letter S, I don't know why I'm losing particles here. That is very strange. Oh, that is speed. Let me see what I've got here. Yeah. Oh, yeah. Okay. That's probably right. Okay. Now let's see. N molecules. Let's see if it allows. No. Let me keep the pressure. Oh, the velocity. Okay. Here I'm. Oh, it allows me to do neons. Let me see. Oh, now it's allowing me to do that. Okay. Well, all right, let me turn off the neons. Okay, so let me keep the pressure at some atmospheric pressure. And, okay, I'll put up enough helium atoms. Let's see if it'll allow me to do... No. All right.
What are the red dots that are...
These are supposed to be helium atoms kicking around in a piston, in a cylinder with a piston on it. And this is the speed of these various particles.
No, I mean the red portion. You see the graph is green and red, that is.
Well, this is the velocity distribution. This is velocity on this axis, speed. And this is the average speed of those particles. And if I increase the temperature, hopefully it'll just increase the temperature, what you see is that if I increase the temperature high enough, if I had an energy level at this S, there's a lot of probability that the particle will be kicked up into this energy level if it was at S. On the other hand, if I lower the temperature, notice how there's not enough energy to kick up into that energy level if I go low enough. And so, again, that level is frozen out. There's nobody can get up into that energy level if I lower the temperature enough. That's the phenomenon of freeze out, as I called it. It's not used in the book, but I think among professionals, that's the concept. That's the word that's used. If you lower the temperature enough, you simply don't get enough particles to be excited. And that is how basically the theory of how Planck explained the black body radiation. Because he said, if I have this box and I heat it up at a certain temperature, and inside the box there are all kinds of frequencies going from 0 to whatever, a very high level, very high frequencies. If I have a temperature of this level, it can, and there are energy levels here separated by an amount h times their frequency. If I have a frequency here much higher, then hf is much greater. If I put in this heat, again fuzzy, about like that, and in fact extending over the average, yes, these oscillators will be excited with some distribution, but you'll get a pretty good amount. Over here, it's not enough to excite a very high frequency oscillator. So these ones are frozen out, and then you will get a distribution of emission where this will be emitted quite nicely, but these won't. And so you get the emission from the black body, which rises up as you, at a given temperature, this is at one temperature, it'll go up to a certain frequency. And then when the KT is not enough to excite those oscillators, which have harmonics, but so the harmonics even are excited of this low frequency one, but in the high frequency one, not even the first level can get excited. And so you put in heat, but none of it is absorbed over here because it can't raise that oscillator into action. So that's the basic idea behind why Planck needed to say that these oscillators, their energy is not continuous, because if the energy were continuous, then every oscillator would get excited. If the energy were actually like this, very close, then even these fellows would be excited and would be radiating. But that is not what we observe, and so he had to stick with the idea that the oscillators have distinct quantum levels. So I think, does that make sense to you as a concept of why we need that? Okay, so let me move on, put that away, and bring up another, the next idea, and that was, I got 2 for 1. Let me do this photoelectric effect. This was the Planck did his work. I think his first paper was maybe like roughly 1898 or 1900, where he proposed the idea that the energy of the oscillators in the black body were not continuous, but had small but real energy differences between them. Okay, now the next step was taken by Einstein. He had a good year in 1905, where he published 5 papers, one of which was, we already talked about, the what he called the electrodynamics of moving bodies, meaning relativity. They were relativity. And he also explained the photoelectric effect. This is actually kind of funny because at that time, I think he was married already to his first wife, Mileva, who was also a scientist working at the Swiss Institute where he had studied. And she was working on the photoelectric effect, as luck would have it. And so probably he got first-hand information over the kitchen table about what they were doing and the data that they were getting, which were very surprising. So you have to give Mileva some credit for this. So, in fact, I think she wanted credit for this. But they divorced soon afterwards when I think he published without her. But the point being that, so what the idea is, let me see if I remember how to work this thing, the intensity. So we turn on light. Now it depends, here's the first experiment is you turn on light, and what happens is that you can measure, now here I have a battery which controls the flow of current through this vacuum. If you turn on this particular light, which is 400 nanometers sort of in the blue, or almost close to the ultraviolet, very, very deep blue, you find particles coming out of this surface, which is maybe not too surprising because light carries energy, so energy is hitting the surface. The electrons are in there. You give some energy to the electrons, and you might give enough energy to pop out. Maybe that's not, it's like you throw a ball into some sand and sand will pop out. It's not so crazy. But the details were not understandable. First of all, what you can do is measure the speed at which they pop out of this material. How do you do that? Well, you put these are negative electrons. So if you make this side here negative, you should be able to slow the particles down. In other words, they'll be repelled from the negative side. So we should be able to, let me see if I can do this. Yeah, I've made it a little bit negative here, and you see how some of them get across, but some of them don't quite make it. In other words, there's a range of speeds coming out of the target. Some of them are pretty fast, and some of them are not so fast. And they turn around. So let's say, okay, these two slow guys never made it. Okay, but you can turn the voltage negative enough that you can stop everybody, right? No, I went too far. 0.8 is too much. I wonder if I can 0.6. That guy made it. Okay, so that's two. I need maybe 0.7. Doesn't seem to want to do me 0.7. Anyhow, it's around 0.7, I would think. I don't seem to be able to be smooth enough to stop it. But 0.8, yeah, pretty close to stopping it. Okay, and the current, as measured here, is 0. So we have what's the idea of a stopping voltage, which by our knowledge already, we know that there's certain a half mv squared. So you can just do the conservation of energy. And the voltage is 0 here, so we have the potential energy plus the kinetic energy coming out of the target. And then we have the side over here where we have potential energy plus kinetic energy. And the potential energy would be E times V. Here the V is 0. We can take that as the 0, and here is the negative voltage. So what we can say is that this thing starts out with kinetic energy. It ends up, when it rides toward this thing, with potential energy equal to EV, and at a certain point it stops. And then we can get what the maximum was. So that is the rule to get what is the maximum speed. It's the E times the voltage you put to stop the last electron, which if I had a better dial or if my hands were steadier, we could get to some pretty good accuracy. But there you have it. Now, so that's the first thing, that we can measure the highest speed. Now, the second thing is what you can do is turn up the intensity. In other words, make the light brighter, but keeping the frequency, the wavelength, the light wavelength the same. So what happens when we turn up the intensity? I'll turn it up full blast, 100%. Well, I don't know if you noticed it, but I think there are more particles coming out. Let me turn it down. Let's see what that. So, but nobody gets there either. So the intensity doesn't matter, except that it changes the number of particles coming out. Now that's strange, because you would think if I put in more light, why wouldn't more electrons come out? I mean, I'm turning up the amount of energy I'm putting in. First of all, the energy is not increasing. The energy is the stopping. So the energy hasn't increased, just the number has increased. That's weird. And I see Albert and Mileva arguing over that. You sure? Did you really measure that? But that's the measurement. This first thing is that the Vmax does not depend on the intensity of the light. Now that's strange, because you would think that as I turn up the intensity, remember the intensity of light that we learned so far is E squared. It goes to the E squared. So you would think that as E goes up, the electric field, you're exerting more force on the electrons. You would think that you're speeding them up more, or you're heating up the surface more, right? If you turn up the light, the surface should get hotter. The electrons should get more agitated by the argument that temperature gives agitation. They should pop out with a higher speed. Didn't happen. Very strange. Very strange. So here you go. There's the intensity effect. Intensity increases the number. Now, you probably know the answer, but you can imagine the people in 1905 scratching their heads over that. Now, the other weird thing is that, all right, let me turn up the intensity to something reasonable. Okay. So you're getting quite a few particles coming out. Let me turn it up way up here. Again, you get more particles, the intensity goes up, but they're not any faster. You just have this maximum speed. They turn around at about the same place. Okay, but now the other effect that the people noticed was that what happens when you change the wavelength or the color of the light? You go from blue down. Now let's see what happens here. Wow. They stop much sooner. Yes, sir.
Why do they not collide when they're both moving back?
With each other?
Yeah, they don't collide with each other.
Well, it's this program that probably this is just a simulation. Yeah, if they were charged, they would probably interact with each other, unless there's very few. If there's a lot of space between them, the electric fields might be pretty. But it's true, they are charged particles, so they would influence each other a little bit. You're right. I don't think they wanted to confuse the picture too much, so they're keeping it simple here. So the point is that if you turn the color down, look where the things stop. They stop over here. And in other words, the stopping potential is much too high. If I really want to get to to stop them, I would have to go down, I think, if I can. Let's see, go down to, let's see what 0.4, you see, they go much better, much further. And, no, I don't want to be positive, I want to be negative here. Little tricky. Well, 20 they make it, just make it, maybe 30. No, It seems to jump in steps of 2. I don't know why. Pardon me? That's a thought. Good thought. Let's try 0.3. Ah. Pardon me? Well, I think it's actually working. 0.3, it's... how about 0.25? All right, well, I think you get the idea. In other words, at the longer wavelength, the stopping potential has gotten smaller. So at, well, again, we're talking wavelength. Higher wavelength, that's what I showed you here. Higher lambda, smaller V stopping. Or, in other words, that, so we have that the V stopping, or the maximum speed, it goes down with the wavelength. In other words, it's 1 over the wavelength. It's inversely as the wavelength, but it is proportional to the frequency because the wavelength and frequency are inversely related. So what you're getting here is that the highest speed is somehow related to the frequency of the light. So let's push that even further. Let's lower the frequency or increase the wavelength from 500. Let me increase the wavelength going toward the red. And let's see what happens now. Okay, these guys are from the previous life, returning to the thing. At that wavelength, nothing comes out, so let me turn up the light, see if I get any more. I'm making it hotter and hotter by the usual ideas, still nothing. So the point being that there is a minimum wavelength needed where, in order to get anything, even at the highest intensity, still nada. Okay, so now at 530 or so, there's a minimum wavelength. So there is a cutoff, you might say. So that's when the V stopping is equal to 0, you have there is a minimum frequency that you have to have, and above that frequency you get something, but below that frequency you get nothing. Okay, so let's let me switch. I hope that's this should not be terribly peculiar to you, but let me go over to this theory that Einstein then came up with. And there's something I want to talk about black body a little bit more, but let's do photoelectric effect first. So here is basically the experiment that we just did. We shine light on a surface. The electrons pop out, and they're collected on this collector actually the voltage here should be negative on this in order to stop them. And you find the maximum speed by finding how much of voltage you have to put on that collector. And the experiment that we just did about the frequency effect is that there is a minimum frequency at which this electrons start coming out. And above that, you have to have above that, you have to have some stopping potential to stop them from arriving at the collector. And you can measure their maximum speed. So the very clear observations are, first of all, and we didn't say that at the beginning, that as soon as you turn on the light, the electrons pop out. That would be surprising if it required that the surface gets heated, because you would figure it would take some time for the surface to heat and the electrons to know it. So that's a little bit surprising. But then the idea is that the maximum energy depends on the frequency above some onset frequency, some minimum frequency. And it does not depend on the intensity. But it turns out that, I didn't show that this minimum frequency depends on the material. For example, cesium, which was, I think, the choice in that particular applet that I showed you, that takes a pretty low frequency. Some things take a higher frequency. But it's the frequency or the wavelength that determines it. And the other idea is that the number of electrons is proportional to the intensity, and not the number, but not their energy. So those are the three observations, and those disagree entirely with what we taught you up till now. So it's not that you should forget everything we taught you up till now. It's just that we have to reinterpret it, I think. I also mentioned here at the bottom that, you see, the idea is going to be that the idea is going to be that there are energy levels inside a material. Here's a surface. There are energy levels where the electrons live. And what's going to be is that the light comes in, and the energy of the light, this is what Einstein said, is proportional to the frequency of the light. The energy is not proportional to the square of the electric field, but proportional to the frequency. That's a new idea, that the energy is proportional to the frequency. Someone, it was not Einstein, called that the photon, because on usually refers to a particle, and this is sort of a light particle. And it means that there are these many particles, each with a certain frequency, which are coming out in this light source, and they each has an energy proportional to their frequency. And what happens is that when that energy reaches an electron, if the energy HF is, again, the idea of exciting from an energy level, if the HF is greater than the binding to the material, which is usually written as phi, a so-called work function. It's just the energy with which the electron is bound to its material. If that, again, it's an excitation, sort of like heat, but it's not heat. It's actually a single quantity of energy, very sharp, proportional to the frequency. And if it's sufficient, if HF is sufficient, it can raise the electron's energy from where it's being held, some level here, to being released from the material, and it comes out with a residual, a half mv squared, the kinetic energy. So that's Einstein's simple picture. The electrons are being held in the material, and the light comes in with an energy HF, so that explains all of these observations. You see, what it says is that the energy is conserved because you come in with an initial energy HF, and there's a potential energy change given by this work function plus the kinetic energy. With the kinetic energy, we measure with the V stopping. So the Einstein equation would be that HF is equal to this kinetic energy, V squared, plus the energy it took to just raise you out of the well. Okay, so that's Einstein's idea, and it tells you that you see it explains this rule over here that if you have HF minus the work function will give you a half mv squared. So that when HF is just equal to the work function, the particle comes out with 0 speed. So that tells you the minimum HF minimum when it's equal to the work function. And then the velocity is 0. So this tells you, that lowest frequency tells you what the binding of the electron to the material is. I'm sorry about that. Okay, let me rewrite that over here someplace. It's the same equation. So what we have the law of conservation of energy. This is the energy in is equal to the potential energy change plus a half mv squared. So when the V is 0, then you get that that's the minimum frequency that will give you emission, but at 0 speed. That tells you the binding energy here. Now, I make the remark that this technique not only tells you the energy here, but electrons also reside in energy levels below this, and you can actually measure the spectrum of energy levels of electrons in a material by just shining in higher and higher frequencies. If you're shining in a high enough frequency, you can get an electron to jump out of a level here. And so you can actually do spectroscopy of the material, of its energy levels, by just shining in higher and higher frequencies. And that is a field of research that goes on now. It's the spectroscopy of solids, the energy levels of a solid, by shining in higher and higher frequencies. So, so I have that comment here. I wonder if getting an arrow will help. This is so frustrating. Okay. Yeah, that's known as photoelectron spectroscopy. Oh, by the way, this is called the photoelectric effect. The reason being that what you're doing is you're putting in photo light, electrons are coming out. And you can do this photoelectron spectroscopy. You shine in various frequencies, scan over a spectrum, shine them in, measure the energy of the electrons that pop out, and that tells you where they came from. Does that make sense? And so you can actually study, and so people do calculations of where the electron levels are in a material, but then they say, are you right or are you wrong? Then they do the spectroscopy of it, and they look at the electrons that pop out. It's a very powerful technique. It goes on. I think they use that even at our advanced light source. That's another place where you can get these radiations. And sometimes you need some very high-frequency radiations to knock the electrons out of very deep levels. If the energy that they're bound is very high, you need a very high frequency to get them out, because the energy is proportional to the frequency. So that goes on. So here's this is, again, this same story. In other words, what you're doing here. What's wrong with this thing? Can't win. What I'm trying to show here. I'm so sorry. I even got knocked out of the whole program. Amazing. What is going on with this computer? I can't even... You know, folks, I'm going to bring my own computer from here on out. This is just unbearable. Don't even seem to be able to get it to work. I think the computer is kicked out. We'll live. So this is the photoelectric effect. And, okay, so the other big step that was made... Yes, sir.
How would this observation be predicted in classical theory?
It isn't. Completely ununderstandable. That's the big... It just doesn't work. I mean, because the question is, how would classical theory explain this? It doesn't. That's why it was so revolutionary. And that is why, indeed, this is the explanation for which Einstein won the Nobel Prize in 1921, was for the photoelectric effect. Because it's a very shocking thing. Now, but you still have to use the classical theory. It has to mesh somehow, because classical theory works very well. They were generating electric waves in 1905. I remember I told you, the Titanic had radio towers on it, so they knew that Maxwell was right to some extent. In fact, Einstein the same year had said, look how great Maxwell is. I can even extend his theory, speed of light being constant and all that. So he was on the side of Maxwell. He admired Maxwell, and he extended Maxwell's theory that light was waves. And here all of a sudden he's coming along saying that light is a particle that carrying energy proportional to its frequency. So how do you mesh those two? Well, the idea is that you can mesh them if you have to reinterpret what the meaning of intensity of light. Before we said the intensity is an electric field, and that's a traveling wave, E cross B, and there's a traveling wave of C, and that's what you learned, and you're right. But now, and then the intensity of the light, namely the energy, we always say is proportional to the square of some amplitude, the amplitude of the electric field, or plus the amplitude of the magnetic field. So now the picture is to reconcile that with particles. This is a nice continuous wave. What we think of now is that intensity, that electric field, is really many, 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 many zillions of little photons. And that it's like a rain of little particles, each carrying energy hf. Each particle carries hf. And you have a big N, hf, is proportional to the square of the electric field. Now, if I had this thing working, it is working now, perhaps. No, it isn't. I may have to restart the computer here. Well, so the point is that in quantum mechanics, what we have is that if a thing is a particle, it has this individual nature, like it has energy. Each particle has a particular energy, like hf, and you have this rain of particles which produces an intensity. At the same time, we're going to see that the particles have wave-like character such that we know that if you have a diffraction grating and you shine these waves on a diffraction grating, you know that you get maxima and minima, right? Now, where does that come from? If these are particles, how can you add two particles and get no particles? If I have particles coming through here and particles coming through here, where do I ever get zero? It's peculiar. It doesn't make sense. But somehow, now here's really the final message. It's from Muhammad Ali. You remember when the boxer, Muhammad Ali, he was very quick on his feet, very fast hands, so he had a slogan, I'm going to float like a butterfly and sting like a bee. You ever hear that? Anybody ever hear that one? You heard it. So that's what quantum mechanics is. I don't know how he knew that. But you float like a butterfly, you float, you travel like a wave, and you interact like a particle. If you think that way, you get the answer somehow. So when things are traveling, they travel like waves. So when they travel through a grating, they travel like waves and they interfere like waves. But when they arrive at the screen, they sting like a bee. So what you get is a lot of stinging over here and no stinging over here. You get a lot of stinging over here and a lot of no stinging in between. So you travel like a wave and interact like a particle. That's the message. And it's true of, as I'm going to show you now, material particles too. Material particles, when they travel like a wave, but when they arrive like a particle. So they, let me try to turn off some of the lights. It may make this a little more visible. And supposedly turn on that. Now, what this is, see, is this on now? Yes. Oh, I've turned on this on. Wow. Okay, now this is one of these old-fashioned cathode ray tubes. Electrons are starting out at the back end of this. They're being steered by either capacitors, which have electric fields which steer them one direction or another, and or maybe with the magnetic coils, where you vary the magnetic field and you direct the particles. And what they're trying to do is have a beam of electrons, material particles, which have charge and mass and all those good things. But inside this tube, they've put little sheets of graphite. So the particles have to pass through the sheet of graphite. Now, if it were a particle, you would think it would just scatter like if I throw an array of baseballs on the floor, they'll bounce in every which way direction and pretty much evenly. You wouldn't expect them to go in one direction specifically. But I don't know if you can see if you're up close enough, you can see that there are rings here on the screen. Now, hopefully, there's kind of visible up on that thing too, right? So apparently what's happening, the electrons are coming through and they're being diffracted just as though it were a wave passing through a periodic structure. This sheet is graphite, is a periodic structure of carbon atoms. And it's a disoriented sheet, so you get scattering of at all kinds of angles in a circle. But there are rings. It isn't as though it's just a smooth blob. It says that there are specific reflection angles, sort of as we said for X-rays off of, like I did the experiment of microwaves off an array of balls. Here, you have not microwaves, you have electrons with their wavelength striking this array of carbon atoms and diffracting in specific angles, preferentially, which is due to an interference effect. So this is a demonstration that material particles have a wave-like character. This was also a big shock. When this was proposed in 1924, and the same argument holds. Now the trick is we have material particles acting as a wave. They're floating like a butterfly. They pass through a grating as a wave. But when they arrive on the screen, they arrive one at a time and cause the interference pattern. This is the mystery of quantum mechanics, how a thing can do both kinds of properties, be localized as a particle when it interacts with something. When you get it, you get the whole thing. But when it's traveling, it seems to travel as a wave. And then you get these diffraction and interference effects. That's quantum theory for you, friends. So, is it 4 o'clock? Oh, okay. So that's the message we'll leave you with, and we'll pick it up again on Friday. Thank you.